Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Dundigal, Hyderabad. In this session, we are taking the case of double-sladed crank chain mechanism, how to do velocity and acceleration analysis, and also in parallel how to find the velocity and acceleration of various links of a given mechanism. So this is the problem I considered here. We have taken the mechanism of double-sladed crank chain mechanism. So the crank OA rotates at constant angular velocity, that is 20 revolutions per minute in anti-clockwise direction, and gives motion to sliding blocks B and D. The dimensions of the various links are OA equal to 300 millimeter, AB equal to the crank, that a connecting rod length equal to 1200 millimeter, and the position, the part of connecting rod, that is BC and CD equal to 450 millimeters. BC and CD. And from the given configuration, what to be found out? The objectives are, there are three objectives are given. We have to calculate by using the velocity and acceleration diagram. The objective one is velocities of sliding, that is sliders B and D, and angular velocity of the link CD, and the linear acceleration of D, and fourth one is angular acceleration of CD. So the objectives consist of the various velocities and also accelerations of the links. That means it is a requirement of acceleration diagram and velocity diagram. So if they don't mention it, also suppose in examination they did not mention anything through the velocity diagram or through the acceleration diagram. So if we can take it as they did not mention anything, so that we can go for the diagrams of velocity and accelerations and solve the acceleration and velocity components of various links. So the solution begin, given that is the acceleration or the velocity, the speed of the link, the crank, that is OA, rotates 20 revolutions per minute. Then omega AO equal to 2 pi n by 60. That is 2 pi times n, 20 by 60. That is 2.1 radians per second. We know the angular velocity OA. Then OA equal to 300 millimeters, that is 0.3 meters. And AB equal to 1200 millimeter, that is 1.2 meter. And BC equal to CD equal to 450 millimeter, that is 0.45 meters. Now we need, if you want to draw the velocity diagram, we have to draw the configuration diagram and redraw the configuration diagram in the ASC scripts where we are going to solve. Then the linear velocity of link OA, that is equal to R omega, that is OA times omega AO, that is 2.1 times 0.3, that is 0.63 meter per second, that is 0.63 meters per second. Okay, that is the manner we have to find out the linear velocities of the links. Of the link OA we found. Then let's go for how to draw the velocity diagram. The velocity diagram, the first step is draw vector OA perpendicular to link OA to some suitable scale to represent the velocity of point A with respect to O, that is absolute velocity or simply velocity of A, such that vector OA equal to 0.63 meter per second. This OA line is OA vector line is normal to the configuration link OA. Next, step number 2. The step number 2 is that from point A, draw vector AB perpendicular to AB, capital letters, configuration AB, to represent the velocity of B with respect to A, and also the sliding motion of the B. The sliding motion of B is linear, translatory motion. That means to draw a parallel line to B with respect to O. This is the line we have drawn. So when both will intersect at point B, so that is the velocity. OB vector is the velocity of B and AB vector is the velocity of B with respect to A. Next, step 3, what to do? We have to mark, divide the vector AB in the same ratio as in the configuration diagram. Point C divides the link AB, okay, in the space diagram. In other words, BC by CA equal to the vector length BC by CA. From that we can know BC value, vector line BC value can be known. After the BC value knowing, mark the point C. Then after point marking, what to do? We have to draw again. Now from C, draw a vector from point C. Now CD is there. The CD, draw a vector. The CD and also slider is moving. The slider with respect to fixed link. The slider motion is the perpendicularly moving. So with that line, draw a parallel line to with respect to C from point C. From point C, what is the parallel line is? Yeah, this is the parallel line from O. Point D, draw a line with respect to fixed link, that is the O. Draw a line, these two lines are parallel, OD and here D with respect to slider. Draw a line, parallel line. And also CD line is there. Draw a vector line from point C to D. Draw a line perpendicular to CD. Then it comes, this is the perpendicular line. So both will intersect at point D. Now join D to O and D to C. This DOD vector gives, or DOD vector gives the velocity of OD vector gives the velocity of D, and CD or DC vector gives velocity of CD. Okay, this is the manner we will find out the velocities. Then after the join point C to point C to point O, that is the velocity of vector C with respect to O. Okay, thus after measuring all these values, we have to measuring the values, the velocity quantities of links are measured. Now by measurement, let us say again, VB, velocity of B, that is VB, where is the B with respect to O? This OB vector gives velocity of B, and VD, that means velocity of D with respect to O. This OD vector line gives length of the OD, that OD vector gives the velocity of D. And if you measure AB length, AB vector, that AB vector gives velocity of B with respect to A. CD vector gives velocity of C with respect to D. Thus we can find out the various velocities of all the links in the given mechanism. Now after finding out the values observed, or velocity of B is 0.4 meter per second and velocity of D is 0.24 meters per second. Now the angular velocity, the point number 2, objective. What is the objective number 2? The angular velocity of D, the angular velocity of CD. What is angular velocity of CD? The linear velocity of CD. This is the CD vector, CD length. That is CD vector line gives velocity of d with respect to c. If you measure that one, the linear velocity is 0.37 meter per second. Now point is that we want angular velocity of CD or DC. Angular velocity, that linear velocity of DC equal to angular velocity of DC times link length DC. If you substitute here linear velocity and the length of the links, then we can measure that omega DC. Okay, that is what we measured here. Okay, now this second objective was achieved. Now what is the third objective? The third objective is linear accelerations of d. So for that, in order to find out the linear accelerations of d, that is AD with respect to O. Okay, that is AD is the combination of AD with respect to O. Then what is the total acceleration that AD with respect to, that means AR dO plus AT dO. So what is that AR dO here? 0 for the slider. Then it is only represents AT dO. That is the acceleration we have to find out with the help of acceleration diagram. Now in this case, let us see here. In order to draw the acceleration diagram, before that we have to find out or calculate the known acceleration components. The known acceleration components from the velocity diagram are radial components of various links. So let us begin. Radial component, radial acceleration of link AO, and radial acceleration of link BA, and radial acceleration of link DC. Whatever known values we have to calculate and keep it aside. So these values are useful to draw the radial components and also helps to draw tangential acceleration components, because tangential accel components, we don't know the magnitudes of tangential acceleration components, but directions are known. So ARAO, that is VAO, V square AO by OA, that is omega square AO times OA, that equal to 1.323 meter per second square. And ARBA values V square BA by AV, that is 0.54 whole square by 1.2, that is 0.243 meter per second square. Whereas the radial component of acceleration of d with respect to c, that is ARDC equal to V square DC by CD, that is 0.37 whole square by 0.45, that is 0.304 meter per second square. How can we know all these values are? All these values are known from the diagram, velocity diagram. This velocity of AB, link AB, the velocity of link CD, the velocity of link OA, the velocity of the link B with respect to O, and the velocity of the link D with respect to O. All these values are known from, yes, velocity diagram. That is a manner. That's why velocity diagram is important in order to find out or draw the acceleration diagram. Okay, now we want linear acceleration of d. So this vector b we find out here, that is 0.4 meter per second. Velocity of vector, that is vector d, that is 0.24 meter per second. From this omega cd equal to vdc by cd. What is the vdc? VDC value we know 0.37 meter per second by 0.45, that equal to 0.82 radians per second. That is angular velocity of the link CD. Okay. Now, in order to find out the first step, we'll go for the first link. Yes, let us begin. Draw a vector OA. How to draw the acceleration diagram? We are going to study here. How to draw the acceleration diagram. How to draw the acceleration diagram. First step, draw vector O dash A dash parallel to OA to some suitable scale to represent the radial component of the acceleration of A with respect to O, or simply the acceleration of A. So now here this OA link is rotating with constant angular velocity. When link is rotating with constant angular velocity, then there is no tangential component of acceleration for that link. Then the total acceleration equal to, that is only radial component of acceleration, ARAO, that is AA, that is 1.323 meter per second square. Draw a vector line, the radial direction of the link OA, that means it's related to configuration diagram or space diagram. I'm using as configuration diagram. This is the configuration. With this OA, you draw link OA. Which direction it is moving? Anti-clockwise direction. We have drawn anti-clockwise direction, rotation. So link OA, this is the first step. Next, second step. The second step is we know the radial components are in both the magnitude and direction. So of link AB. So radial component of link AB is A dash X, that is radial component 0.243 meter per second square. So with this radial direction of link AB, draw a line. That is the second step. With this link, we have to draw a perpendicular line, that is the tangential component of acceleration of link AB. But we don't know the magnitude, but we know the direction. So draw a line. That is the direction. That is step number 2. Okay, but we don't know where it is intersecting. Then what to do? We have to go for second step. Okay, that is draw a line parallel to the B. The B is moving in a tangentially, that means linear direction. There is no radial component. Draw a line with respect to fixed link O. That is parallel line. That is OB dash. This OB dash intersects the tangential component of acceleration of AB, that is XB dash, at B dash. Now, after joining this intersection B dash, draw a line A dash B dash. This A dash B dash is the acceleration of link AB. Acceleration of link AB means it is the total acceleration of link AB. What is the total acceleration? Both the radial component and the tangential component of accelerations. The sum of radial component and tangential component of accelerations. Then it is called acceleration or total acceleration. You simply call it as acceleration. Alright. Of link A dash B dash. Now, we found just now OA dash, AB, that is the acceleration of B, and acceleration of link AB. What are the remaining links are left? CD left and D also left. So the direction of rotation of D is in linear direction. That means there is a tangential, that is with respect to O. This is the O, and D. How to write? The OD. The direction is, OD is what? The acceleration of D. You draw a parallel line to the sliding motion of the slider D. This is the point we have to start. Next step. That is third step. This is the fourth step. Next. Then fifth step comes, mark the point C and draw a line which dash, that is C is related to CD. The CD is having radial component. What is the radial component? This is the radial component. CY dash. C dash Y. For the tangential component. Next step. And this tangential component is intersects to the sliding motion of the slider D. This is the slider D. This OD dash and YD dash intersects at this point. Now, after that, what to do? You join OC dash. Okay, that is the final step. OC dash line. If you have to join. Thus, this OC dash, O dash C dash vector of acceleration vector gives the value of acceleration of C. with respect to O. And OD dash, the length of the vector, acceleration vector O dash D dash, the length of the acceleration vector O dash D dash is acceleration of D with respect to O, or simply acceleration of D. Next, the length of O dash A dash is the gives the acceleration of link A with respect to O, or simply acceleration of OA. Next, if you measure the length of O dash D dash over OC, next OC dash O dash C dash, that gives the acceleration of C with respect to O, that is simply AC, acceleration of point C. Next, if you measure the length of CD, OCD, again if you join C dash D dash, one more line, okay, that gives, that is the length of velocities, or that is acceleration of C dash D dash, means acceleration of D with respect to C, ADC. Thus you can find the accelerations, or you can measure the accelerations of all the links by measuring the vector lengths from the acceleration diagram. This acceleration D, AD, that is vector O dash D dash, that is equal to 0.6 meter per second square. And our final objective is, from the acceleration diagram, what we want? Angular acceleration of CD. That is, angular acceleration of CD comes from tangential component, that is ATDC, that is vector YD dash equal to 1.28 meter per second square. So angular acceleration of CD, that equal to alpha CD equal to ATDC by CD, that is ATDC equal to 1.28 meter per second square by 0.45, that is 2.84 radians per second square. Thus, we found all the objectives of this problem, that is double slider crank chain mechanism. What are the objectives? Angular acceleration of CD, that is 2.84 radians per second square. What is the third objective? Acceleration of D, that is with respect to O. Acceleration of D with respect to O, that is 0.6 meter per second square. So like that, we have to find out all the values, what is required, what are the objectives were mentioned in the problem. Okay. Let me again share the completely. Now here we can, what is the step 1? The step 1 in this is, what is the step 1? Pay attention how to do the acceleration diagram. This O dash, A dash is the step 1, A dash X is the step 2, and X B dash is the step 3, and A O dash B dash is the step 4, and both will intersect at a point B dash, that is a point B dash is the step 5, and joining A dash B dash is step 6. Next, what is the step 7? The step 7 is the point marking the point C. Marking the point C is the step 7, and after joining O dash C dash is step 8. Then from C, drawing C dash Y, step 9, Y D dash, step 10, and D dash comes by intersecting O dash D dash, step 11, and after that this D dash point is the step 12. And if you want to join CD dash, you can also join the link, that is C dash line. Okay, the C dash line can become. Thus you can join CD dash here. That is also step 13. Though thus we can find out the complete accelerations of all the links of a given mechanism. So these are the 12 steps. And how we have drawn in velocity diagram, how the velocity diagram is, What is the step 1 in velocity diagram? In velocity diagram, step 1 and 2. First we have to draw OA, that is the step 1. Okay, OA is the step 1. O dash A dash is the step 1. Next, AB is the step 2. And step 3 intersects the point at B. Then after that, C point C is the step 4. And drawing the normal lines, there are 2 lines are there. BD dash is the step 5. And OD step 6 intersects at point D. And after join C with O, vectors OC is a step 7. This is the 7 steps diagram. So thus we have to draw the both velocity and acceleration diagrams, and we can find the various values of velocity, both velocity and acceleration values of various links of a given mechanism. So second problem, if you go for it, let us go for next case. We are going to study the second case, that is one of the mechanism that is called toggle chain mechanism. Okay, it is a single slider. It is a single slide but double crank mechanism. So this toggle chain mechanism is a single slider double crank mechanism. So let us begin. This in the toggle mechanism, the given data is, it is a double, that is OA is one of the crank and CB is another crank. How to, the slider D here, it is the slider D. This is a link AB and also BD. There are double cranks also here. Double cranks are, there are 2 cranks OA and CB. And there are 2 fixed links, that is O and C. So let me read the problem and what are the objectives we can know, and what are the dimensions of this toggle mechanism. The slider D is constrained to move in a horizontal path. The crank OA is rotating in the counterclockwise direction at a speed of 180 revolutions per minute. That means it is a constant angular velocity. That means there is no tangential component of acceleration. For this link, OA consists of only radial component of acceleration, no tangential component of acceleration. Increasing at the rate of 50 radians per second square. Now acceleration component also given, that is alpha of OA, 50 radians per second square. The dimensions of the various links are as follows. What are the dimensions of the various links? Are OA equal to 180 millimeter and CB equal to 240 millimeters, AB equal to 360 millimeters and BD 540 millimeter. For the given configuration, find number 1, objective 1. There are 2 objectives are given here. Velocity of the slider D. We want velocity of slider D and angular velocity of link BD. Second objective, acceleration of slider D and angular acceleration of link BD. So here velocity of slider D and the angular velocity of link BD. This is a link BD, can be found by using velocity diagram. And objective 2 can be achieved by using acceleration diagram. So here we have to draw both velocity and acceleration diagrams in order to achieve these 2 objectives which are mentioned in the problem. So here this configure, we have to redraw again. Let us begin. We have to redraw the configuration diagram in our answer script before going to solving or before going to draw the velocity and acceleration diagrams. So how to start? Let us begin. That is link OA. The link OA, the speed, that is 180 RPM, that is 180 revolutions per minute. That is omega AO equal to 2 pi n by 60. What is 2 pi times n? 180 by 60. That is 18.85 radians per second. That is OA. Then OA equal to 180 millimeter, and that is 0.18 meters. And one more thing, CB is 240 millimeters, that is 0.24 meters. AB 360 meters, that is 0.36 meters. BD equal to 540 millimeters, that is 0.54 meters. So the linear velocity of the link OA, that equal to VA times VA equal to V equal to R omega. That means R is here, link OA times omega AO. That is 18.85 into 0.18. That is 3.4 meter per second. Okay. This is the linear velocity AO. So with this, try to solve as a homework, and based on this problem which I solved before in this lecture, that is double slider crank chain mechanism. If you apply that methodology for this problem, we can complete or accomplish these two objectives which are given in this problem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.